Welcome to the video on E2 integration for E2 processes. So in this video, we would like to understand how we can extend the integration theory we developed with respect to a Brownian motion to a larger class of processes. And the processes we would like to consider today are so-called E2 processes. So this brings us, so this is part of chapter 4. Let me directly begin by defining what we mean by an E2 process. This definition 4.1. Okay, here we go. So we have a stochastic process, and this stochastic process is called E2 process. If it has the representation that x can be written as an initial value, which is supposed to be a real number, so plus the Lebesgue-Stieltjes integral. So we integrate the process A with respect to time, so ds, and as a stochastic integral. So here we have another stochastic in the process B, which we integrate with respect to Brownian motion. Yeah. All right, and now we need to choose the conditions on A and B in a way that this here is all well defined. So what we want to have that A and B are functions from the sample space omega, so our completed probability space, to R. And we want that they are adapted, right? Otherwise, this is not well defined here. They are measurable processes such that we need to have also some integrability conditions in order to have this integral to be well defined. And what we want, it's enough that the processes are in H log. So we assume that if we integrate A to the absolute value of A in time, this has to be a finite number with probability 1, right? This ensures that the first integral here, the Lebesgue-Stieltjes integral, is well defined. And we want that stochastic integral is well defined as well. So as I said, we want that B is an H log. So we assume that if we take B square, this is integrable over time. Right? This is almost sort of finite, meaning with probability 1, this integral stays fine. Okay. So as I said, well, why do we do this? Because this condition here ensure that this function B is an H2 log. And this means the stochastic integral here is well defined, and by the other integrability assumption on A, the Riemann integrals or the Lebesgue integral is also well defined. Okay. And well, to have a useful representation, we actually want that this representation of the E2 process X is unique. And actually, it turns out that if we have this representation is indeed unique in the sense that A and B are almost surely uniquely defined on the product space. So this brings us to our first lemma, which is part of the problem sets. So if we have an E2 process, X, be an E2 process with, we have now two representations. So X is equal to X0, right? This is the definition. So we have this function A, and and b so that we can represent the process in terms of the integrals here. But now we assume that there's another representation, so x0 tilde plus a tilde, so the integral over L a tilde and then integral over b tilde now with respect to the Brownian motion. And, well, this holds for all t and t. And we want that the initial conditions are the same. Here we go. Then we actually know that a is equal to a tilde and b is to b tilde p times lambda. So this is the Lebesgue measure almost surely. So in the product space, they are almost surely the same. And as I promised you, well, you can find the proof, though better you do it yourself, on the problem sheets. Here you go. Okay. So here, yeah, got to underline the definition of ITER process. So what we want to do now is to develop or extend our ITER integration to this class of ITER processes. And at the first step, we want to extend the notion of quadratic variation to the class of ITER processes. Right? So far, we have defined the notion of quadratic variation for local martingales, but this in ITER processes in general, not in local martingale, because we have here this drift term given by the Riemann status integral. So, proposition for any ITER process. And we always assume that our ITER process has this representation, so given by A and B. An ITER process xt 0 to t, the quadratic variation of x is given by, well, okay, to be precise, first we need to say what we mean by quadratic variation for the ITER process. So this first sign here is a definition. Well, as before, we take the limit along any zero sequence of partitions, and then we sum up over the square increments, restricted to the interval 0 to t of x. Right. And now this is the statement of the proposition here is this is actually equal to the integral from 0 to t of b square integrated with respect to ds. Okay, so since this is a definition, let me underline it by green, with green as you should. Okay. So, I mean, this proposition has, actually two statements, right? The first one is saying, okay, this limit exists. And the second one is, well, that this is we have this equality so that we can represent the quadratic variation with respect, as an integral of d squared. All right, so that's the main proof we want to do in this video. Oh, proof. Okay, so recall So what we have is x is equal to x0 plus bt. Yes. Plus, okay, I always wrote it the other way around, so let's start with a. Yes, a plus. So this is just our representation of the process. And now what I want to do is, okay, let me call this here, this process A. And the stochastic integral are just M. Okay. What we know is this is your a martingale, a local martingale. And this is has finite variation. Okay. So because what we want to show, I mean, how we have to continue is we want to show that actually this finite variation term doesn't matter. So this just disappeared. It's not contributing to the quadratic variation. And this local martingale has exactly the quadratic variation as claimed in the proposition. So this is where we start. So these are the two steps we want to do. So step one is to show if I take the quadratic variation of m, then it's just given by the integral from 0 to t of b squared integrated with respect to ds. Okay, so that's step one we want to do. Okay. First, I mean, we have quadratic, we have a local martingale because it's a, maybe I should, right? Since B is in H2 log. Okay. So how do we show this? So first thing we do is we take a localizing sequence. Sequence tau n for our local martingale, right? This is localizing such that if I look at the stop process here, this is a martingale, right? I mean, this exists because we know it's a continuous local martingale. And what we also want is that if we look at this corresponding integral process stop with respect to tau n of e squared, this is uniformly bounded in T. So we can just simply take the stopping time, making sure that we stop if m gets bigger than n, or this integral goes bigger than n. And so then we have achieved it, in, the goal for our localizing sequence. Okay. So what we also see here is, if you look at the right-hand side of what we want to prove, is we know this process here, square, starts at 0, right? If we set t equal to 0, it's 0. It's increasing because when we're integrating here a positive function, a non-negative function, so if you, no, this is not decreasing. And continues. Okay. So the only thing we need to verify in order to show that this integral process here is the integration is that if I look at the stop process to the power 2, and I compensate it here, so I subtract the stop integral process, this is a martingale for every n. I need to show this here is a martingale. Well then. Okay. What does it mean here? This means, okay, what we want to show is, and this is what we want to show. If we take the conditional expectation of the stop process square minus time t, and then minus it at time s, and we subtract here the integral from s tau n to t tau n. Yes. And I condition this to the filtration at time s. This has to be 0. Right? This is, I mean, equivalent to say that this process is a martingale. Now we have here, I mean, we know that m is the process, the stop process here is a martingale. So what we can move is we could move the square to the outside here, right? Because we have done this move, the trick several times. And this is just meaning the cross terms cancel out here because we have this nice condition on FT. FS, sorry. Okay. Here we go. I mean, this integral is as before. All right. So what we want to do is to show that, I mean, this term here is, this term has a conditional expectation of 0. So we want to condition with respect to fs. So what we do is what we want to understand is if we take indicator function of s, because I mean, this is in fs, because this is to what we want to condition. We want to understand this term here, right? This term minus n square. And I condition it on an event in fs. Okay. Cool. So what is this? This is nothing else than m at time t minimum tau n minus s multiplied with indicator function of a. If I restrict again to the event that tau n is greater or equal than s. Right? If it's less or equal than s, then this different is 0 anyway. So this equality still holds. Okay, but now I can express this as an integral. Condition on a of the event, okay, tau n is greater or equal than s. And now I conditioned again on s to t, right? Because here s and t. And I plug in the definition of my martingale m. So m is just given as the integral of b with respect to the Brownian motion. So what do I get here? Oh, this is r, like my integration parameter of b r indicator function of 0 to tau n, right? Because I have here also the upper bound of time of r br. Okay. So why do I do this? Well, I want to show that this is 0. So this means I want to show that the conditional expectation of here, this difference to the power 2 is equal to the conditional expectation of this stress integral, the Back-Stich's integral. Okay, so let me look at here these different. Okay, I should. Right, condition to set A in Fs. Okay, and then I take the expected value. So now I use this calculation here. So I have here the integral square, right? I can pull in. I shouldn't use green. Right, I can pull in this term here, in here. Doesn't matter. Because I mean, Fs squared, the 1 or the 0, I mean, this has no effect. So I can write here the integral. So now I use the equal, then I have the integral of indicator function of A. Now let me put the indicator function a bit together. So, right. Right, dr, dr, dbr. Okay, and now I can use each isometry, right? I have a normal, I mean, Riemann Sum integral. I have a stress ET integral, and I know, since thanks to this localizing sequence, that this is in H2 as tau n local localized this, right? Right, this is an H2 log, and now I localize with respect to tau n. So this is in H2, and I can apply E2's isometry. E3, which tells me is okay, I have here my integral. I can indicator function of A, and then I have the indicator function of S minimum tau n, T minimum tau n, R, and now I have, okay, B, R, and everything to the power 2, and then I have the integral with respect to ds. Well, okay, and now let me, okay, I can calculate this integral a bit further, so let me write the integral boundaries. I mean, you can pull out this set indicator function of A, right? Because this indicator function of A does not depend on R. So I can pull it out. I have the integral, okay, let me plug in the integral boundaries, which I have expressed here with the indicator function. Okay, that's nice. Okay, and now I have here B square as R, dr. Yeah. And now I look what I want to show. So what I know now, since I can do it for all elements in AF, that the conditional expectation of this term here, conditioned with respect to Fs, is equal to the conditional expectation of this term here with respect to Fs, right? And now I scroll up. So this means exactly what I want to show is this term and this term here cancels to 0, conditioned on Fs. Okay, so this is exactly what we wanted to show. So if I take the quadratic variation of this stress integral here, it's just b square. Integrate the integral of b square with respect to ds. All right. And now I want to come to the second step, which tells me well, if I add now this finite variation term A, so if I really look at the quadratic variation of X, then the quadratic variation is not changed. So I again get my integral of B squared in time. All right. So let's take here some t in time, and I take a zero sequence of partitions. The zero sequence of partitions. And what I want to assume, without loss of generality, that what this t little t here is in pi 1, right? I can always add it. It actually doesn't matter because we have here continuous function. Okay, so this is nice. And j, as before, these are all intervals in my partition Fn such that they're in the interval 0 to t. Right, this is Jn is just a restriction of my zero sequence of each partition to the interval 0 to t. Okay. So I want to show that the limit of n going to infinity of the square increments, so the sum over the square increments of all elements in Jn and x squared go to this integral from 0 to t of b squared. Yes. And of course, this all should hold in probability. All right, so let's show this. Okay, so first thing we do is we decompose this sum here in three terms. So so if we look at the sum of all j's and jn of the square increments of x2 squared, right? We can use binomial's formula to get three sums, because this here is equal to, right, m plus a. So this is our composition. So what we get here is sum of all the square increments of m, the sum over m over the square increments of a, and all the cross terms. So the product of the increment of m and the increment of a. Okay. All right, so let's look at these three terms. So first thing, by step one, what do we know? Well, the first term converges as we want. Right? If we look at the limit of n to infinity of the first sum here, this goes to integral from 0 to t of p squared integrated with respect to ds. Okay. Okay, so what we need now is to show that the other two terms go to 0. And this actually holds in probability. Okay, so let's come to the second term. So if you look at the second term here, well, we can estimate it rather brutal by pulling out the supremum over all these elements in the j's nth partition of the increment of a, right? And then I still have the sum. So in each sum, I mean, I can estimate the term more than once with the supremum of all terms, and then I have still the sum of all elements in the partition of the increments of A. Okay. Well, this here can be estimated by the finite variation norm, right? So semi-norm. This is can be estimated by this, and this means, so this is a finite variation. This stays here bounded, and this goes to 0, n goes to infinity because we have a continuous process. So this means this goes to 0, even almost surely. Okay. A is continuous. Okay. Okay. Last term. And now we have the product of the increments of M and the increments of A. Well, here we can use just Cauchy-Schwarz inequality. So how can we estimate this? So we have here the sum of all the increments of M to the power 2, and then we get here 1/2, right? This is what Cauchy-Schwarz is telling us. And here the same for the increment with respect to A. And what we know now is, well, this here goes actually to the quadratic variation of M, which is should exist, and this goes to 0 by, well, our last observation. Cool. So what we see is that, well, overall, this goes to 0 as now, and now let me make here square roots, the square brackets, so we're done, as n goes to infinity. So what we see is, if we come back to our decomposition, the first term goes to the integral we claimed it should go through, and the other two terms go to 0. So this finished our proof. Cool. All right. Okay, so we have constructed and defined the quadratic variation of an E2 process, and now let me come to the actual E2 integral. To extend E2 integration, I want to make the following observation. Observe. Okay, so what do you do? Okay, let's start very simple. So let's say F, right, from the product space here, omega and 0t to R is continuous. Adapted, and bounded. Right, so we make all the assumption to make our life simple. And now I make the following observation. So let us look at the Riemann Sum Approximation, which we understand. And actually we want that this is somewhat true. So I want that this goes to, I mean, if I make the mesh size going to 0, so if I write these Ti and Tj, I mean, they get closer and closer to each other, and then I want that this converges in a suitable sense to my integral with respect to the E2 process X. Okay. So let me okay, what is this? I mean, we can plug in the definition. So this is nothing else than, no, the, right, if I Ti minus X at the point Ti minus X at time Ti minus 1. So we have the integral from Ti minus 1 to Ti of a integrated with respect to ds plus yes. All right. Okay. And now we can rearrange this. So this is nothing else than the integral from 0 to t of the finite sum. So I have no problem with integration. Right, and then I have here ti plus 1 multiplied with a s, and now I have the indicator function from ti plus 1. Minus 1 to ti. Okay, so that's the first thing. And the second thing, well, I have still my stochastic integral, which I need to, stochastic terms, which I need to understand. So I do the same trick. So I'm localized here my integral and then put the sum inside. So what do I get? Okay, dbs. All right. So what we observe here is, okay, if we make let the mesh size going to 0, so that this position goes fine and fire. Now this goes to fs, right? This is okay, and then I have still the as. Okay, and this goes to dbs ds. All right. So this brings us to the next definition, right? So if you want to define this here, I mean, if we want to this goes to f integrated with respect to x ds, whatever this means. We can just define it. I mean, these two integrals are well defined, so we just make the right-hand side to our definition. This is what we do in the next definition. This is definition 4.4. First, we need to specify what's the class of integrants. So all x denotes all adapted measurable functions f from the product space here, omega 0t to r, such that so we want that the Riemann Lebesgue integral is well defined. So we assume that f multiplied with a is well defined. So it's a finite integral, and if we take f times b to the power 2, this is finite, both pure almost surely. Okay, so that's what we want to define here. And now we can define for this class of integrals f the Lebesgue their integral. So for f in L, we define the integral by okay, so the integral of f with respect to x is given just by the integral from 0 to t from f multiplied with a ds, right? This is a classical Lebesgue integral, and then the integral from with respect to ds. Right? This is exactly what we have observed here in green, that this is what we want to make to our definition. All right. This is for 0 to t. Good. So this just maybe this here is well defined as FB FBS is an element in H2 log, right? This is how we choose the assumption here. Okay. All right. Now let me conclude this section by a remark and a lemma. Let me start by the lemma. So following lemma 4.5. So if I have an ether process which has no Riemann Lebesgue integral involved, so if the process A here is integral to 0, I can make some nice observation of it. So if I so if I take an ether process, such that so x is now equal to x0 plus an ether integral with respect to Brownian motion. So this means the process A is just 0, right? So I have no Lebesgue integral involved. And I want that f is integrable with respect to x. So it's in L. Okay. What are my two claims, which are now straightforward conclusions from what we have developed for the ether integration with respect to Brownian motion? The first thing is, if I look at the integral process, right, this is a continuous local martingale. Yeah. And second thing, okay, let me write it below here, is if if the integral from 0 to t, if of f square ds b square ds is finite, then ethos isometry holds. What does it mean? So if I look at the integral, so if the L2 norm of the integral of f with respect to dx, then what do I get? If this is the same as the expected value of the integral from 0 to t of fs, yes, and then integrated with respect to the gradient variation of the ether process x, right? And we know that this exists, and I can also make this small t and small t. This holds actually for all t. Right. Right. Okay. Why is this integral here well defined? Let me make a remark, which is remark 4.6. So what we know is, since this derivation here is non-decreasing, leading process, this integral here, 2, is Lebesgue-Stieltjes integral. And well, we can use the associativity of the Lebesgue-Stieltjes integral to see that if I look at this integral here, I can apply the last proposition, which is proposition 4.3, which tells me this is so plus plus the associativity of Riemann integration. Oh, okay, Lebesgue integration. Oh, Stieltjes integrate. Right. All right. Okay. Okay, so let us briefly prove the proposition 4. The lemma 4.5, which is now just recalling all the results we have learned in case of stress integrals with respect to Brownian motion, right? But the integral of the E2 integral with respect to an E2 integral, I mean, can always be reduced to the case of integral with respect to Brownian motion just by how we have defined it. Okay. So proof. Okay, first, we want to show that the integral of f with respect to an E2 process, if a is equal to 0, then this is again a local marking. Okay. So if we have now an L in f in integral function, so what we get is that this is in H2 log. Or just by the definition, and this means this here is a local martingale, an even continuous local martingale. And if you want to look it up, this is what we have shown in theorem 3.15. All right. Second proof is not easy as the same. So what we want to show is that we have an E2 isometry if we have the right integrability assumption. And the integrability assumption was that if the integral from 0 to t of f squared, yes, dpt is finite, well, then we actually know that that this term here, f times s ds, is in H2. So what we can do is we can apply Ito's isometry, right? Which allows to show, right now, if you look at the L2 norm of the integral of f with respect to the E2 process x, this is by definition, so let's plug in the definition of the integral here, which is nothing else than the, no, I want to show it for every t. So let me make a little t. And this just means I need to sneak in an additional indicator function. Okay. All right. And now I can apply Ito isometry, which says I can here basically pull in the vector to the exponent 2. And this means I get here an integral with respect to ds. Cool. And well, here we'll use again proposition or the remark we just have derived, right? So let's remark. Which number was it? 4.6. All right. So this is exactly the Ito isometry we wanted to show. So this concludes. All right. You see, I mean, Ito integration for Ito processes is not hard anymore since we developed it already with respect to Brownian motion. Thank you for watching the video.